Hello, Java programmers. Let's talk about binding. The big idea is we can decide what method we are going to invoke or call at 2 points in the life of a program. We can decide when it's compiling or building. We use those terms interchangeably here. Or we can decide when it's executing. When we decide at compile time, that's called static binding. The decision is made, it cannot change, and it happens before the program runs. It happens, might be invisible to you, depending on how close you pay attention, but when you click that run button, two things happen. Eclipse builds or compiles your program, and then it runs it. And you're really only concerned about the second one. If it doesn't build, you get a squiggle, and hopefully you've already eliminated all the yellow and red lines before you click the run button. But the second thing that happens is your program runs or launches or executes, and that's the part you're interested in, and that's what you really associate with that green button. However, there is a build process going on there. And in this case, Eclipse converts your program into some intermediate format that we refer to as bytecodes. That is the thing, the little file, the entity that is movable between systems. So I can give you a bytecode file of my program, and Java, the Java runtime, the JVM, can execute that bytecode file. The source code file that you write using Eclipse is converted into bytecodes, and then those bytecodes are executed by the JVM. The other kind of binding is called runtime or dynamic binding. And whenever you see dynamic in the context of a computer programming language, think of runtime or execution time. That is exciting to us because we can make changes on the fly to the way our code behaves based on the way we've created our classes and how the classes inherit from each other. And this lets us write very, very flexible and useful code because it can adapt to new things without us having to go in and make a lot of changes to it. Now, we've seen many, many examples of compile time binding to this point, and we'll look at that right now before we move on. Compile time binding, we might also refer to that as overloading a method or polymorphism. The methods are the same in that they have the same name. They have overlapping scope. They may have exactly the same scope, or they may have scopes that intersect. But they differ based on the parameter list. We're differentiating one method from another when they're in the same scope by the parameter list, not the name. And you've done this before, you probably just didn't realize it. On the next slide, here's our motivating example. We have a really simple exercise where the main method calls a method called hello. However, there are two methods called hello. Is this a compile error? Is this a build error? No. This is perfectly fine because the methods differ by the parameter list. And that's the way Java views the differentiation of methods. It considers two things, the name and the parameter list together, and that makes those two methods different. I took the code off the slide and I built an Eclipse project out of it. And we can use that as a discussion point. I encourage you to do the same thing. It shouldn't take you but a moment. I have a class called main. It's in a package called main with a lowercase m. It's the same code that was on the slide. I did add a package statement. That's not necessary here. This is just a quick and dirty example of a concept. And we're going to talk about this. The first thing to notice, there are two methods called say hello. As we just discussed, they are not conflicting with each other, even though they are in the same scope. They're both in the same class. They don't conflict because they have different parameter lists. The method in line 16 takes a string as a parameter. The method in line 12 takes no parameters. Eclipse has no problem, Java has no problem deciding which method we are invoking in line 9 because there are no parameters in that method invocation. Therefore, it is going to use the method defined in line 12. And we can demonstrate that by using our friendly debugger. Remember, the debugger is absolutely crucial to your development. You need to master it. I'm going to set a breakpoint in line 9, and then I'm going to run in debug mode. That means click the little bug button in the menu bar, toolbar, button bar, whatever it is. I never know what to call that thing anymore. We don't use the green run button anymore. We use the green debug button. I don't know what kind of bug that is. Doesn't look too scary. When I click debug, it builds the program. So it converts it to bytecodes. It starts to run, and then when it gets to the breakpoint, it pauses. The line highlighted in green has not yet executed. It's waiting for us to provide further instructions. And we have a couple of choices. If you look under the Run menu, you can do a step into. And I encourage you to press the function keys. I'm not pressing function keys because you can't see me do that on my keyboard. Therefore, I'm using the menu. But you're much more efficient and a better developer. You get done faster. You'll have a lot more job satisfaction, and you'll impress the heck out of people if you use the function keys instead of the mouse. The mouse slows you down dramatically. I'm going to press step into, and before I do that, just take another peek. We're sitting on line 9, waiting to execute line 9. I'm going to press step into, and that's going to tell Eclipse to follow into the say hello method. The next line of code that it executes will be line 12. We can then demonstrate the execution flow, and we can show that it does do static binding, and it's already decided what method to call based on the method signatures that we provided in this class. I'll click the Run menu and I'll say step into, and it hits line 12, and then it jumps into the method and goes to the first executable line of code in that method, which is line 13. If I do a step over now, and before I do that, just stop and think, you do not want to do a step into print line. That's not your method. That's part of the Java library, and there's no reason to step into that. Chances are it probably won't even let you, and you just get a nasty message. But there's no debugging to be done. There's nothing to be learned right now by stepping through Java library functions. So do a step over, and it executes the print line. Look in the console window. You can see that it printed hello. Also notice in the console window, console tab, that the terminate button is lit. That's a visual indication we are still running the program. It's still executing. But we're executing one line at a time because we're in debug mode and we have control over that. If you're done, which I am because I've proved my point, I can terminate this debug session by clicking that terminate button in the console tab, or there's a terminate button in the button bar tab menu thing at the top. They both work the same, and they will take you out of debug mode, terminate execution of the debug session, and put you back into edit mode again. And this is one of our challenges, keeping it straight. How many times have we started the program, and how many times have we stopped at a breakpoint? You can have the program running multiple times, and it gets very confusing. You need to be careful and take yourself out of debug mode when you're done debugging. Don't simply forget where you are and go back into the editor and start making changes and then run it again, because you're going to look up and you're going to have the program running 5 times, which is a big mess. And then you'll eventually start getting cryptic messages from the debugger, and you won't know why, and you won't be able to reproduce it. You have to keep it straight in your head when you need to close the debug session. We all go through it. We all make that mistake. But keep an eye on that red button, and if you need to click terminate to take you out of debug, then do that when you're ready to do that. We're demonstrating then what we call static binding, also referred to as compile time polymorphism. There's one of those OOP terms that we talked about. The next thing we're going to do is discuss dynamic binding or runtime polymorphism, which is a much bigger deal. And I want to encourage you to be able to differentiate between those two things. Differentiate between runtime polymorphism and compile time polymorphism, because they are different. And that's a question that you'll be asked. That's one of those job interview questions. A lot of times the interview process consists of a phoner, and in the phoner you're going to get a technical person who would probably be rather doing anything than talk to you. They'd rather be writing code or doing something productive at work, but they've been assigned the job of talking to you, and they may have a list of questions to throw at you, like what is OOP, what is inheritance, and they may say what is polymorphism. And you should be prepared to say there are 2 kinds of polymorphism, runtime and compile time, and then talk about each one in a sentence or 2, because that's what they want to hear, is that you have a grasp of these concepts. And if you can't talk the talk, then they're not going to give you a chance to walk the walk. And that's a lot of companies do that initial phoner to filter out people that aren't necessarily qualified for that job. And it's scary because they're asking you questions and you're not going to know all the answers. They want to hear what you do know, and they also want to hear how elegant and you are in explaining things that you don't know anything about. And it's rough, but you'll get through it. My first job interview when I graduated undergrad was with Texas Instruments, and in those days the companies came to campus. I hope that comes back again. They set up shop in one of the buildings, and then you made an interview appointment. You went in and talked to a representative from the company. You may have had 2 or 3 or 4 interviews in a day. And this was in the spring of my senior year. We're looking to graduate and get a job and start getting paid. I went into the TI, Texas Instruments interview, and I was just terrified, just scared to death. I'd already had a co-op job. I'd had plenty of job interviews, but this was just a big deal. And I sat down in the room with a little table and just me and the interviewer, and he asked me some questions, and he could tell I was terrified. I was probably 20, 21. And finally he looked at me and said, "Is this your first interview?" And I said, "Yes." And he said to me, "Don't worry, there'll be more." And I know he meant well, but it sounded like he was saying, "You're not going to get this job." But that's what happened. I didn't get any additional interest from them, which was fine. I probably didn't want to move to Texas anyway. But it is a scary process, and the more you do it, the easier it gets. Let's add one more thing to our example of static binding, just to demonstrate, and I think this is a confusing point for some students, that this parameter name doesn't have any significance except semantics. You don't have to preserve it or carry it back to somewhere. And let me just show you an example of that. I can change that name. Now I have three methods called say hello. The first method called say hello in line 12 doesn't take any parameters. The second method called say hello in line 16 takes a string. The third method in line 20 also takes a string, and I tried to differentiate between the last two methods by changing the name of the parameter, and that doesn't accomplish anything. Eclipse is just looking at the data types and the position of those data types, what order they appear in the parameter list. Therefore, changing the name of the parameter does not differentiate one function from another. Think about that in a little more depth. It still wouldn't provide any sufficient information to tell that function from another one just by changing that name. So hopefully that clarifies a little the use and the application of that parameter name. It's just for your purposes. It should have some semantic meaning. It should carry some useful name, but it doesn't have to be used to differentiate one function from another. I could just as easily call it X, which I would be coming to your house and crying if you named a variable X. That's just a terrible name, but structurally I am allowed to do that. Also notice that I got a bunch of errors when I duplicated the method signature across two methods in the same scope. I got an error that says duplicate method. That's a good error message, but the fix is probably a disaster. The fix offered by Eclipse is rename method say hello. That's probably not what you wanted to do. It might be, but it's probably not. Another illustration of why simply blindly taking the fix is rarely a good idea. Let's say that I realize this is a duplicate. I'm just going to change this to float. Now I'm good. And I can change this back to name. This is fine. I have three functions at the same scope, but they differ by the parameter list. They are all called say hello. That's perfectly good. And they differ from each other because one takes no parameters, one takes a string, and one takes a float. That's the way we work. That's the way we roll. The inclination is to change the names of the methods. Say hello with no, and I'm exaggerating here, parameters. Say hello with string. Say hello with float. And that's just an unmitigated disaster because they're all the same method. They do the same thing. They just take different parameters. So boogering up the names simply to make the names different for no other reason than to make the names different is a bad idea. Let polymorphism do its job. And since all those functions should do the same thing, make them have the same name. Just differ by the parameter list. Now in C#, looking ahead, C# has the capability of assigning a default value to a parameter. And then if you don't provide the parameter, it will, at compile time, put that value into it. But that's generally something that a lot of coding standards frown on. It's just an opportunity to introduce error into a program, and Java doesn't support it anyway. Hopefully that was a good intro to compile time binding. And as you write your code, think about how this is useful. You might already realize, and I hope you did, that we did this like crazy using constructors. We did it last week. We overloaded a constructor by creating one constructor that took no arguments and another constructor that took a couple of arguments. And since constructors are at the same level of scope, that was compile time binding, and Eclipse decided which one to invoke based on the parameter list. Back to the slides. We've discussed compile time binding. Make sure you have a good grasp of what that is and why it's useful and what the shortcoming is. Remember, the shortcoming is it happens at compile time. Once you ship that code, it can't change. Runtime binding is a decision that's made when the program is executing. And the trick is that we can create a base class from which all our other classes inherit, and then at runtime invoke a method that is in the derived class but using a base class object. You're hearing me use all kinds of terminology. Keep emphasizing you've got to learn the terminology. When I say base class and derived class and inheritance and invoke, you've got to learn to talk this talk. Because if you can't, someone will give you some instructions. You need to do this in your program. You need to create an abstract base class with a overridden polymorphic dynamic binding runtime interface, object-oriented, three-dimensional pizza class, and you're going to be like, I don't know what that is. Learn the terminology. Don't shoot past it in the book. Stop, read the book carefully, define all the terms in the sentence, make sure that you can derive some meaning out of what the book is telling you. You're not reading for entertainment, you're reading for education. What we're going to do then is we're going to create a superclass. And in the superclass, we will have a kind of a bookmark to a method. And then that method will be fulfilled or implemented in the derived classes. Now the substitution principle applies here. And I'll talk about that just a little bit. We'll probably get to that later on in the semester. But I want to use it as an opportunity to introduce a concept that includes the substitution principle. In order to introduce that principle and in order to avoid writing a whole bunch of code, I have provided for you an example, and I want you to drag it down into your workspace. So we're going to do an import. And we're going to import using a project from Git. You don't need an account to do this, but you should have an account by now. And I'm going through the import process. I'm going to do a clone URI. That's my repository source. The URI I provided for you in Canvas. If you look in the module, it's a program that I wrote that I put in my code repo. I'll poke out the repo for you right now. I think I have it up here. There it is. There's the repo. The project is misspelled. It says Substitution, but if I tried to rename it right now, it would be a lot of work. I just left it as is. So this is a demo of the substitution principle. The substitution principle is attributed to a computer scientist. I'm looking for her picture. I think it's on Wikipedia. There it is. I'm getting out of hand. Click more slowly. There she is. Jane Liskov. Barbara Liskov, sorry. I don't know where I got Jane. And Barbara introduced this at a conference. If you haven't been to a conference, I encourage you to look for opportunities to go. It's a great way to get cutting edge information and talk to your peers. You can learn things that aren't published in books, and you can interact with other people in your field. So if you're interested in a conference, start searching around online. There are plenty of conference schedules available. Maybe you can find one that's close by. Maybe you can get with me and I can direct you to some that might be useful. But Barbara introduced this concept in 1988. It's been around for a while, and it's been covered ad nauseum on many, many, many websites. And of course, I jumped in with both feet and I created an example for us, because the best way to learn something is to write code about it, especially if it's programming. The substitution principle is part of a greater whole called the solid principle. I encourage you to look that up. We don't have time to cover it here, but solid is 5 programming principles. And actually, they're design issues. They're not specific to Java. Any object-oriented programming language can adhere to these principles. They're considered good code if you follow these. There is on YouTube, I hope you've all heard of YouTube, a personality Uncle Bob, I think. Yeah, there he is. Uncle Bob Martin. Uncle Bob is a lecturer, a programmer, and the guy that came up with the concept of solid. He has extensive videos posted. You can hear him talk all about it. He goes on and on and on. You can decide what you think of him, develop an opinion. Again, this is something that is part and parcel of what we do. It's part of knowing about our field. Therefore, watching him speak, listening to him speak, will give you a more well-rounded personality in computer programming. And then when his name comes up at lunch with all the other developers, you can say something about Uncle Bob. But we're not going to watch his video today. We're just concerned about Liskov substitution. I have created this very simple example just to show you the mechanics of it. I'm not going to talk about enforcing it or why it's good and how it can be violated, but I have got an example just to show you how we can do it in our program. You're going to pull down that project from Eclipse or from GitHub, sorry. You don't need authentication. I already have mine here. I want to point out that the authentication changed recently. You don't just put in your GitHub password anymore. You have to go get a token. You can Google that because you can't authenticate through Eclipse, through the Git plugin, unless you've got that token from the github.com site. Therefore, make sure that when you're ready to start authenticating, meaning you're ready to start interacting with your account and pushing changes to your repos, then you're going to need to get that token. And I found out the hard way the other day when my authentication logic stopped working that GitHub had changed the way they do things. And this is probably something that arose out of the purchase of GitHub by Microsoft, I assume. But it really provides a tremendous amount of flexibility now, because I can issue that token to you and I can limit what you can do on my site based on the token I give you. It creates an entire security structure that's actually kind of neat. Anyway, you don't have to authenticate to do this exercise. I put in the URL. The Git plugin in Eclipse extracted the name of the repo from the URL. It did a little bit of research in the repo and it found there is a master branch, which there has to be. Every repo starts with a master branch, and there are no other branches. There's no decision to make here. And then I have a problem because there's already a repo on my machine with the same name. Because what it's going to do is clone that repo onto my machine, and I'm just going to put an X at the end of this. You don't have to do this because you should not have this repo already unless you're stalking me. But you can ignore that X. It does a little bit more investigation of the project. It finds an Eclipse project inside the repo, which is good. We were hoping that would happen. All we have to do now is click Next because it's set up to import. And here's the last chance to change your mind. Don't have to change anything here. Click Finish. And you get in your workspace a brand new shiny project, which is all the code that I wrote in my repo. You now have a copy of it. You can do whatever you want with it. Any changes you make will not be reflected in my repo on the website. This is totally your repo locally on your machine. So let's look at how I demonstrated this principle. Start with the classes. And the classes are named exactly what they represent. I have a class called superclass. And remember, that could also be called, we've got so many variations on the terminology. Sometimes we also call that a base class. A base class and superclass are the same thing. This superclass has a property. Doesn't matter what it is, but I gave it a name. Again, the semantic meaning of the name is just indicative of what it represents, a property in the superclass. I'm not modeling anything in the real world. I'm just modeling a concept of OOP. It has a constructor that takes one argument. By presenting this constructor, I override the default constructor, which takes no arguments. However, I elected to also provide an implementation of the default constructor. I'm sorry, I didn't. My bad. This is the getter. I don't know what I'm thinking about. This is the getter for that property. Below that is the setter for the property. Okay, this is a traditional structure that we're used to. A getter and a setter and a constructor that takes an argument. No problem at all. It's a happy little class just sitting out there in space minding its own business. The next class is called subclass, and we could also characterize this as derived class. This guy inherits from the base class. Using the extends syntax, that means that subclass is a derived class of superclass. Subclass inherits from superclass. Again, terminology, very important. It has its own property. That's called subclass property. It has a constructor. The constructor takes two parameters, one of which is going to end up in this class. The other one is going to end up being shot up to the base class in the form of a call to the superclass constructor. So this is a invoke superclass constructor. and we're passing that property which is intended for the superclass constructor in the call to the superclass constructor. And then we've got a getter and a setter for the subclass property. That's my hierarchy. One base class, one derived class, one property in each class, getters and setters. Should be pretty vanilla to you at this point. The only thing out of the ordinary about this is that we're not modeling something. We're just creating classes for the sake of classes. All this is exciting, but we need to do something with it. We have still to demonstrate the Liskov substitution principle. Let's do that now. Go to the main. In the main, we create an instance of the superclass, and we there it is. We create an instance of the superclass. Notice that we do not instantiate it. Notice that there is no instantiation here. We declare. We do not instantiate. That's kind of interesting because to this point, every time we declared an instance of a class, we almost always use the new keyword to instantiate that class. And I said that wrong. Every time we declare an object of a type of class, then we always use the new keyword to instantiate that class. I used instantiate wrong. But we didn't do that here. All we have is an empty variable, and we know what data type it is. But it doesn't refer to anything. It's just empty. On the next line, we declare and instantiate an instance of the subclass. And that's fine. That's going to create a subclass object, store the reference in the variable mySubclass, and the two properties will be passed in and stored appropriately. So we're good to go. Finally, in line 15, after all this work, there's the demonstration of the Liskov substitution principle. We take an instance of the subclass and we store it in a base class reference. An instance of the subclass is stored in the base class reference. And then we can use that superclass reference, that base class reference, and invoke properties off of it. Invoke methods off of it. And we know that in the base class there's a method called getSuperClassProperty, so we can call that. I have a line that's commented out here. If I uncomment this, notice I have an immediate headache. I can't invoke the derived class method from the base class object, even though that base class object refers to a derived class instance. And the error is not very helpful. It just says that that method is undefined. And what it really would be nice to say is, hey, Bill, you're trying to invoke a derived class method on a base class object, but that would be problematic for Eclipse to figure that out. We've demonstrated then in line 15, we can substitute a derived class object into a base class object and then have it still kind of work. All the base class things still work. And this is one of the premises for dynamic binding. The ability to do this lets us do dynamic binding. And that's why we went over this today. And when we look at our dynamic binding exercise here in a moment, I'm going to show you this line of code again. And I want you to think back on the fact that we're using the substitution principle to get this done. Before we launch into our example, let me just reiterate that what I've shown you here in this little substitution principle project is just the mechanics of substituting. The principle stipulates that when you do this, then the base class should still function correctly. This new object that we are messing around with, my superclass, should still work. And now work is a concept that only applies at design time, meaning that I should be able to do this in my code and everything should still run the way it did before. We're not near talking about how to look at code and understand if the principle is being followed. I'm simply showing you the mechanics for doing it. And if this was a design class, we would spend more time on that principle and how to design software that work that way. Just showing you the mechanics of a substitution. The next thing I'd like to do is close all of these tabs, save them. Notice I didn't even run this, by the way. I don't even care what the output is. I just want you to understand the mechanics of what's going on here. If you have to get out your debugger and step through this, do so. If you have to look up these terms and define them on a piece of paper, do so. If you have to hold a discussion group at Panera to understand these terms, do so. I guarantee you with 100% certainty that if you understand the terminology, you will enjoy this topic much more. When you read something, you will know what it says, and when you have to implement a solution, you will understand what your directions are. So don't skip over the terminology. Saving my work because I don't like to throw things away, and moving on to a brand new project. Let's say new project, and I will say this is a Java project. We're not extracting anything from a repo. We're going to start from scratch, and I'm going to call this runtime binding because that's what we're demonstrating. Refer back to the slide one more time, slide 6. We have to create a superclass, a base class, and then we will inherit a couple things from that to let us illustrate runtime binding. I have my project. I'm going to launch into creating some classes. I wouldn't be doing this in a production environment. I would have some kind of design document, and I would do a lot of pre-planning. And I will call this package factory. Our premise is that we have a factory or a distribution center or a warehouse, anything with some devices in it. Distribution centers are interesting to me. Conveyors, scanners, diverters, packers, all these things in my distribution center are computer controlled. Motors, pumps, and they have to be started and stopped. So if you think about from a macro perspective, and this is probably certainly not how it works, but someone walks in the morning and hits a switch and the whole factory turns on. And then at the end of the day, someone hits a switch and the whole factory turns off. And that would be a really nice goal, and that's what we're going to try to implement here. I mean, factories don't work that way. Shutdowns don't take place that elegantly, but we can certainly model that in a program. Our factory is, let's create a device class, okay? DEVICE. This is a generic device. It's going to be our base class. It doesn't exist in the real world. Devices are specific, a particular pump, a conveyor, a scanner, a diverter. But they all have a base class. They all have common features and functionality and properties and methods that we could consolidate into this base class. Again, doing design work. What are the common features of all of the devices in our plant? They would aggregate into this new class. And we're going to make this an abstract class. Okay? Nobody can instantiate this class. That's why it's abstract. We're not going to let anybody accidentally make a device object because there is no such thing in our factory as a device object. But it is a good place to consolidate all the things that all our devices do. And notice the abstract keyword when I create that class. If you forgot to check the abstract checkbox, you can just type that in. All right. Now we know that it's time to think about all of our devices. What do they have in common? I will assert that every device has a startup and a shutdown. Therefore, we should create methods that we can call and we know that we'll come back and figure out later by individual device how to do these things. I don't know how to shut down things and start up things, but I know that I'm going to have to do it. This is, maybe you think of it as a bookmark or a placeholder, and eventually it will be provided. And Eclipse isn't happy because the way I wrote it is syntactically incorrect. I can't just make a placeholder like this, but I can if I make it abstract. By making it abstract, I'm saying later on in a derived class, someone will write this. Later on in a derived class, someone will write this. That's what abstract means. I don't know what it's going to do, but somebody else will. And then I would fill out this class as necessary with other properties and methods that might be common to all of my devices. We're talking about design here. I hope you're following along. There's my abstract class. I could put a Java doc in here. Model the properties and methods of all our devices. Whoops. Keep in mind that long term, I don't even know what these are going to be. Devices could be added to the factory next year, and this class has to account for that. You have to be really, really general here. That doesn't mean we might have to refactor the code, but we make an attempt to get it right in the first place. There's our base class, and we refer to this as an abstract base class. I'm going to save that. I'll leave it open. I might want to refer to it later. Let's go back and create another class. And this is going to inherit from our device class. It's not abstract. It is something that will exist in the real world. We'll just call it pump. We might get a little more specific than that, but for these purposes, a pump is a specific kind of device. It's specific enough. It doesn't need a main. We haven't got to the main yet. It's not abstract. It inherits from device. It's in the same package. Click Finish. Now, look what happened. Amazingly cool. Eclipse implemented the startup and shutdown methods that were abstract in the base class. Again, more terminology. The abstract methods in the base class have to be implemented in the derived class. I'm committed now, because I inherited from device, to fulfill those abstract placeholders, those bookmarks. Eclipse made an attempt to do that for me. It just went ahead and created a stub, an empty method, and I go in and immediately delete these to-dos. I don't use to-dos in this class. They are useful for bigger projects. And then I have to decide what to do here. What happens when the pump starts up? I don't know. That's too hard. I'll just make it print something. System.out.println. I am a pump and I am starting. Do the same thing for the shutdown. I am a pump and I am shutting down. Again, somebody later who knows about pumps, who's studied the pump, who has the software from the manufacturer of the pump, could go in and provide that logic to make that happen. But we don't know. We don't have to know. Let's do one more. Let's add another device to our factory package. Same process. This will be a conveyor. Make it inherit from device. And notice by default, backtracking a little, it says which method stubs would you like to create. The inherited abstract methods box is checked. That's why we got those stubs. And that's a good thing because we'd have to type them in anyway. But we'd like to demonstrate the problem if we don't provide them immediately. I'm going to uncheck that box just because I want to talk about it. Let's look at what we're doing now. We're saying we're creating a class called Conveyor. It inherits from device. So device is the base class, Conveyor is the superclass. No, device is the base class, Conveyor is the subclass or derived class. And since since device has two abstract methods in it, they are going to have to be implemented in the derived class. But they are not going to be implemented. We're going to get an error. Let's watch and see. There's my error, and this is what you get, and you need to recognize it and then just go fix it. The error says the type conveyor must implement the inherited abstract methods. That's just what we were talking about. So since Eclipse didn't generate those stubs the way it did in the pump class, we got an error. And it'll fix it right here. Add unimplemented methods is a quick fix for that. Select it, and then look, you get the same code that you got when you let Eclipse do it earlier in the process. And then I can paste in that print statement and edit it a little bit. I am a conveyor and I am starting. I am a conveyor and I am shutting down. Good. We have three classes. We've created a hierarchy. Make sure you hit save to get those error messages out of the way. We need a main. Let's create our main according to our architecture. New class. Class is called main. It's in its own package just to keep it separate. It's easy to find that way. select public static void main. Unless you'd like to type it in yourself, have Eclipse create that stub for you. Click Finish. There's my main. Get rid of the to do. Okay. All right, let's start instantiating and declaring and using our class hierarchy. This should be fun, right? Let's make a device. Device D. I can't do that to you. I can't call it D. It just hurts too much. Device. Got a problem. I declared a variable called device that is of type device with a capital D. That's the data type, but this class doesn't know what that is. Because they're in different packages, you add the import statement and the error goes away. Eclipse does it for you. And that's a declaration, remember. Okay. That's our declaration. And the next thing you might want to do, because we're always mentally connecting declarations and instantiations, the next thing you might want to do is try to instantiate, and we can't. Device equals new device. Can't do that because device, the class device, is abstract. You cannot instantiate it. That's not going to work, but that's okay. We're still where we want to be. We just can't do this. Cannot instantiate abstract class. Just can't do it. Sorry, Charlie. Out of luck. Let's make a couple of let's make a pump and a conveyor. So pump equals new, and I'm going to declare and instantiate at the same time now. Declare and instantiate. Do the same thing for conveyor. I'll just expect you to follow along with me here. Conveyor and conveyor. We had the same problem with the pump class and the conveyor class. The main doesn't know what they are. So we can let Eclipse fix it by adding import statements. You could just as easily typed in these import statements, but I didn't. I let Eclipse do it. And I think you can shorten this. Can you say import factory.star and then comment these out? Does that work? Yeah, that works too. If you start ending up with huge numbers of import statements and you find that inconvenient, you may want to just comment those out. I think those also collapse though. Therefore, if you get too many, you can just collapse that little section using Eclipse. Eclipse, the code editor, is very good. And you can just remove those. We'll put that back the way it was. That was conveyor. And then I'll collapse this. All right, this is good. We have two instantiated devices, one pump, one conveyor. We have a device object, but it's empty. So it is of type device. It just doesn't point anywhere. It doesn't refer to anything. If I try to use it, watch. If I say system.out.println device dot shutdown, I got several problems there. One of which is what's wrong with println. My bad. I don't have to print it. I just have to call it. Sorry. Don't need the print. Okay. If I try to call it, I get you haven't done any initialization on this variable, and that means you didn't instantiate it. That's what that means. So we can't do that. And we don't want to instantiate it, so I don't want to call this anyway. I'm going to take that out, and I'm going to put a comment here. Eclipse ERR device not initialized. Okay, just as a reference that we can't do that. But let's see what we can do. Here comes the substitution principle. Get ready. So device equals pump. Yay. I did it. Finally we got there. Substitute. S-U-B-S-T-I-T-U-T-E. Substitute. Exclamation point. A base class object refers to a derived class object. How about that? How about that? That's awesome sauce right there. That's the substitution mechanism that we saw in that other example a couple minutes ago. Well, what value is that? Okay, the value is, watch what we can do because it's an abstract method. Device dot shutdown, if you can spell it. It works now. It works now. And you can say what method is being called. You should be able to answer that in this simple example. You can tell me that it's going to call the pump dot shutdown. Exclamation point. This is getting good. We're almost to the point of runtime binding. We're almost there. You can see that. You can tell what it's going to call because we stored a reference to the pump object in the base class variable / object thing. Run that and you'll see that you get the pump message. I am a pump and I am shutting down. So cool. We're going to make it even better though. This is going to get better in just a minute. If you're excited, if your heart is racing, take a minute, pause the video, go get a Mountain Dew and come back. Let your heart rate settle because it's going to get so much better. But wait, there's more. Let's make a whole collection of devices. I mean, our factory does not consist of just a pump and a conveyor. That would be a sad little factory. Our pump has many, many, many devices. Therefore, we need some way to manage them as a group. I can't manually create 10,000 pump variables and then write 10,000 lines of code to start them up. That would be horrific. But I can put them into a collection and then manipulate the collection as a whole. Okay. Let's use an array list because it's old and clunky, but it still works. Device. My devices equals new array list device. The error message is because it doesn't know what an array list is, easily fixed by importing the array list class. No problem. It just adds another import statement. Good. All the errors are gone. We declared and instantiated. It's got nothing in it. It's an empty array list of devices. Note that it is an array list of abstract class objects. We can do that. We can create placeholders for abstract things. Look up at line 13. Remember, we couldn't do line 13. We could not instantiate an abstract class, but we can create a collection of abstract class placeholders. Here is the good part, but not the goodest part. This is still just getting to the goodest part. Let's add something to myDevices.add new pump, call the pump constructor, and then let's add a conveyor, and then let's add another pump. We have 2 pumps and a conveyor in our factory now. This is a substitution principle happening in fact. Every one of these is a substitution. Does that rate an exclamation point? Nah. No, it doesn't. It does rate being spelled correctly though. I cannot spell that word. I don't know why. S-U-B-S-T-I-T-U-T. Maybe it's got too many T's in it. I don't know. Doesn't rate an exclamation point. It rates a period. Okay. This is going to grow and grow and grow. We could add more pumps, conveyors, create motor classes, create diverter classes, create scanner class, electric eye, printer class, all the things that need to be turned on and off. Time clock, lights, door locks, fire suppression, who knows. But eventually we need to turn all these things on. All this hard work is going to pay off because we can step through this array list using an enhanced for loop. We can step through this array list using an enhanced for loop. Watch. Well, I know you're watching. For paren device D in my devices there's our enhanced, I did it wrong. I'm thinking C#. There we go. For device D colon my devices, C# uses the word in when they have an enhanced for loop. Now, this is runtime polymorphism right here. Get ready. Sit down, take a deep breath, turn off Spotify. Here we go. D dot shut down. There it is. This is run time binding, and this rates 2 exclamation points. This is the coolest thing ever. Every time it goes through this loop, it gets the next value in the collection. And then at runtime, it decides whether it's a pump or a conveyor. Once it's decided, it calls the appropriate shutdown method. That's runtime polymorphism. And that's a big deal. Of course, you want to see it run. And there it is. Let me try to get that a little bit bigger. Okay. The first line of output is from this. Let's comment that out. It kind of clutters up the screen. There's our output from the loop. The first thing in the collection was a pump. The second thing was a conveyor. The third thing in the collection was another pump. All of that output came from 31. That one line of code generated all that output. Let's take you through the process of enhancing this. All right, we talked about how we don't have to change the way we shut down the factory. All we have to do is add more devices. Let's back up, and we come in on Monday morning. Everything's great. We've got our can of Monster and our jelly donut, and we sit down at our desk and we find out a new device has been added to the factory. It is a motor. Go back to your factory class, a factory package, sorry. Add a new class. We're going to create our motor class. It will inherit from device. How about that? It is not abstract. We do want to generate the inherited method, so you can let Eclipse do that for you. Check that box. Click Finish. There's our motor. We just need to add those two print statements that tell us that it is a motor. I'll just copy those from Conveyor, Control C. I am a motor, and I am starting, and then Control V, I am a motor, and I am shutting down. Okay, there's our device. We did it. Nothing to it. It inherits from device. It implements the abstract methods defined in the device class. Go back to the main and let's add a motor to our collection. My devices dot add new motor. You know what happens now. It's going to complain. It doesn't know what a motor is. It also complained because I spelled devices wrong. All you need to do there is add the import statement for motor. I didn't touch the for loop. I did nothing to the for loop. Eclipse and a Java will automatically figure out, actually Java, will automatically figure out what class is being processed and what shutdown method to call. Here we go. Let it rip. Our output now includes the motor. I'm going to stop and take a drink of water. I'm so excited. That was refreshing. I hope this is interesting to you. This is a concept that you will use quite a bit if you look for the opportunities. It's a concept that you'll implement in your homework. And it's a concept that is possible to break. So let's see if we can break it. How about that? What could go wrong here? What could go wrong? Let's try, and let's add something else to our factory. New class. Let's say that there is something in our factory that the other developers weren't really sure how we implemented our architecture. They just threw in a device. This will be a scanner. When the boxes go by, it scans their barcode and decides whether they should go to Michigan or Ohio. It doesn't inherit from device. It's going to just inherit from java.lang.object. It's a mistake. We blew it. We weren't paying attention. All right. There it is. There's no mention of inheritance, but I can still go in and put these start, up, and shutdown methods into this new class. I can still put them in there. They are simply not overriding any abstract base class methods. And I'll just copy the two methods from the pump class and I'll throw them into my scanner because I'm not really sure what I'm doing. I'm going to get an error because it says that they're overriding something in another class, but they're really not. And I'm going to make the error go away the way that Eclipse suggests. Remove the annotation. That makes the error go away, right? It's like I made my mom stop yelling at me. Doesn't matter if I did it the right way or not, but I can do the same thing in the shutdown and the errors are gone. I know I need a startup and a shutdown, but I didn't inherit from the base class, so it looks kind of right, but it's not right. It's not in that class hierarchy of devices anymore. Now, can I go back to my main and can I add one of these little guys to the device collection? My devices dot add new scanner. Can I do that? Well, first of all, it doesn't know what a scanner is. We better import that scanner class into our program, and we better pick the right one because there are multiple scanners in a Java library. So pick the right one. And look what happens. It says you can't do that. Since scanner is not inheriting from device, and we promised our program that this would be an array list of devices or things that inherit from device, we cannot call or we cannot add a scanner. So that doesn't work. Isn't that good? We can say cannot do this because scanner does not inherit from device. And that does not write an exclamation point. All right, we just illustrated then someone trying to take a shortcut and adding something to our project that violated our architecture. I hope this got you interested and you can see different ways to apply this. We'll add a couple more comments and discuss it maybe to clarify it a little bit. What's happening at runtime here? At runtime, the JVM decides what type of device D is. Okay? Why am I saying okay? You can't answer me. We know that D is a device base class object, but because of the substitution principle, it could have been in its previous life any of those other inherited classes. And it doesn't know that. The program doesn't know that until it steps through this array at runtime. There's no way to determine that before we run the program. The JVM, not Eclipse, you don't have Eclipse anymore when it's running. The JVM looks at each instance of D, each object in that array list, and decides what data type it is. And then calls the shutdown method on that particular data type. I hope you found this interesting. Please email me with any questions or post them in the FAQ. Visit with me during office hours. See you next time.